Our next speaker is KAIXIANG ZHUANG, and he will be talking about the compressibility of conceptual information across the human cortex.
Okay, thanks for the kind introduction. My name is KAIXIANG ZHUANG from ISTBI Fudan University. Today I'm going to talk about my research study about the compressibility of conceptual information across the human cortex. So in everyday life, we consistently interact with various objects. As we come across many similar items, our mind naturally goes into what we call concepts, like a cat, a dog, or car. So moreover, these representations can be further organized into higher order categories such as animal and transportation. Together, these form our semantic knowledge that enable us to attach meaning to our world. Even though we think of concepts as separate with clearly defined boundaries, our mind doesn't necessarily process them in this manner. Behaviorally, a recent study found that conceptual information can be compressed into a small number of continuous dimensions that can be effectively explain semantic similarity across thousands of concepts. Similarly, at the brain level, prior study found that conceptual concepts can be represented as locations within continuous semantic space that is smoothly mapped across the cortical surface. So the first few dimensions of this semantic space seems to reflect key variations of conceptual information, such as a shift from living to non-living things. So altogether, these findings revealed how elegantly the brain can utilize low-dimensional manifolds to compress and organize complex conceptual information into continuous semantic space. However, the distinct contribution of individual cortical regions to this global information compression remains poorly understood. It also remains unclear whether there are any organizational principles that govern this compression. So to address this question, we first had to ensure that we collected enough neural responses across a wide variety of objects. In a continuous recognition task, we showed participant images of everyday objects from the same stimuli set, which included over 22,000 objects images across 8054 distinct concepts. So each concept contained 12 exemplars. Based on human judgment, these concepts were grouped into 53 high-order categories like animal and transportation. Moreover, each concept was associated with 66 human-annotated interpretable dimensions. For example, the dimension could be how colorful an object is or how valuable it is. Overall, we employed a dense sampling procedure across 20 participants, each completing 5 sessions of ACB-style data acquisition at 70 fMRI for a total of 60 rounds for each person. For the preprocessing of the neural image data, we used the minimal ACB preprocessing pipeline complemented by additional procedures such as ICA fix and MSO surface registration methods. Finally, we employed GEM single to extract single trial neural response to each object and average them within concepts. The resulting matrix represents cortical responses across all the concepts that can be used to investigate how the brain compresses conceptual information into low-dimensional semantic space. For this, we use PCA as it features our redundancy and retain key components that reflect structure of the data. Specifically, PCA loadings here represent how the entire cortex compress and organize conceptual information. Based on this PCA loading matrix, we developed an index called global compressibility, which is the product of the reconstruction arrow of the top n components and their importance. Simply put, this index tells us how strongly each vertex local pattern reflects the cortical-wise compressed conceptual information. So next. High global compressibility indicates the neural representations in a given brain region encode low-dimensional abstract information that is shared across the entire cortex. Low global compressibility suggests that a given brain region encodes high-dimensional detailed information that extend beyond the shared global dimensions. Projecting this index onto the cortical map revealed a clear contrast. While regions primarily located within the default mode network, such as the posterior parietal and medial prefrontal cortex, showed high global compressibility. Regions within the ventral visual pathway, such as the medial and inferior temporal cortex, displayed low global compressibility. As expected, regions with high global compressibility only use a small number of core dimensions to explain variance, while regions with low global compressibility maintained explanatory power across a broader range of dimensions. Beyond the two extremes, however, when we break this map into 20 bins, we can clearly see how the explained variance gradually changed across the entire cortex. So it's worth pointing out that global compressibility picks up on meaningful neural structure, not noise. It shows no spatial correlation with the brain's noise settling map in these talks, nor does it correlate with the global signal-to-noise ratio. So having derived the global compressibility map, our next question was to investigate whether these regional differences reflect underlying organizational principles that govern the cortex-wise compression. To answer this, we started by applying representational similarity analysis. By constructing a concept-by-concept similarity matrix, we are able to obtain the representational pattern for each of the 20 bins derived from the global compressibility map. When we look at the pairwise similarity between global compressibility bins, we notice something interesting. Bins that have closer compressibility values generally show more similar representations. So moreover, when compared to non-models, the representational similarity revealed a sharp deviation between high and low compressibility regions. It is showing higher within group similarity as opposed to between group similarity. So these findings suggest that global compressibility captures a gradient structure in the cortex-wise organization of conceptual information. So to understand the potential coordinate roles of the different regions, we performed segmented decoding of these 20 bins using NewSync database. We found that both ends of this map are associated with topics related to long-term memory and mental imagery. However, only the high compressibility regions are linked to more complex cognitive functions, such as mentalization and decision-making. Building on these results, we suggest that the two ends of the compressibility map correspond to different types of conceptual representation and mental activity, from abstract processing at one end to detail-oriented processing at the other. Moreover, we aim to characterize the representational property of brain regions at both ends of the global compressibility map. To this end, we applied PLS analysis to link regional representations with 66 interpretable dimensions. As expected, regions displaying high global compressibility can be explained by a small number of behavior-derived components, but regions showing low global compressibility require a high number of components to describe their activity pattern. Finally, we visually illustrate this point. We projected all concepts into a two-dimensional UMAP space based on the PLS loadings from those significant dimensions, and color them according to the 53 higher-order categories. The larger the halo, the greater the distribution error of the category along a given axis. So we can see that core categories are consistently captured by similar representational geometry, regardless of the level of compressibility we look at. However, these high versus low global compressibility regions also show distinct profiles. High compressibility regions emphasize cross-category similarity with cluster distribution and increased error variance, while low compressibility regions maintain precise category distinctions with clear boundaries. So in summary, here our investigation has shown that high-dimensional conceptual information can be compressed into low-dimensional semantic space, and that this compression is not random. A global compression framework shows that the brain processes concepts gradually from detailed representation in the inferior temporal cortex to highly abstract ones in the core default mode network region, such as the PCC and angular-drives. While primary conceptual dimensions are shared across the whole cortex, distinct brain regions maintain varying level of fine-grained detail in their representations. Okay, so that's all. Thank you. Thanks to Dennis first, who lead the whole projects, and all our lovely lab members and collaborators. Thank you so much for your listening.
Right. Well, we've got one question here,
Yes.
which is, we have a lot of information about spatial and language processing from animal studies. How do your findings extend what we already know? I mean, I guess it would be more like the spatial processing from...
If I get this question correctly, I think so. What we previously know is, so spatial one or semantic one, semantic information can be compressed into some low-dimensional manifolds in the cortex. For example, in the ventral, ventral visual pathway. So it's something we have already know. But something we don't know is whether there are some regional differences in the contribution of such, global-wise or local-wise compression. So our study aims to contribute to highlight the regional differences of this, compression in the construction of the low-dimensional semantic space. So yeah, it's the differences, I think.
Thank you. Any other questions? Oh, time?
We still have 1.5 minutes. If you don't mind, I might ask.
Yes, definitely. Thank you.
So you're essentially saying to us that the default mode network is involved in abstraction.
Yes.
Do you think this could just be an artifact of getting people to lie still in a scanner and let their mind wander?
You mean mind wandering?
Yes.
Yeah, I think so. So in my own opinion, so the default mode network kind of like an abstract pointer. So but the detailed information is encoded in regions such as the inferior and medial temporal lobe. So it's also very important to the episodic memories, right? But for the default mode, it's kind of like an abstract pointer. So it gives you a rough direction to go. And then once you, point out to this direction, you can then, grab more detailed information from those, low compressibility regions. So it's definitely relevant to mind wandering, I think, because mind wandering, yeah, it's like the direction to go. Yeah, it's my own opinion.
Then thank you very much, and let's move on to our next speaker.
Thank you.